Okay, now we start with a limit. Okay, so limit. Some essential concept for limit, so that you can more focus on is we can say that limit this is exists if we have this definitions. Okay, and from limit we can also relate it to definitions on derivative. Okay, or we can say that it's okay. And limit, when you deal with the limit, we how to evaluate limit. First, check or substitute the value, right? And the second, if it's 0, 0, then it will become indeterminate forms. The implications for indeterminate forms will be, you can try to rationalize, factorize, or if it is trigonometric, you can use trigonometric identity. Or from the chapter 4, we know that we can apply the L'Hopital rule. Now, if we given a question that is just this, and since it's trigonometric, we can think of some identity, or if you want to directly answer, you can just try to check whether it's indeterminate forms or not. So whenever you have limit, the first thing you need to check is check the limit. Check, and it's 0 over 0. Right? So if you want to directly answer, you can use L'Hopital rule if you want. Meaning, L'Hopital means that the top and the bottom need to be derived each one. Okay. X. still check, still I think we're still using L'Hopital. Not sure how many times we are going to do this, but check. Then this will be 4 cosine to x. Now I think we can evaluate the x. So check all, and then we will have 2 over 4, right? 2 over 4 or 1 over 2.
Well, Professor, you get 4 cos 2x because of Tian rule, right?
Yes. So because of this 2 sine 2x, we have 2 and then the dx of sine 2x, which is 2 multiplied by 2 cos 2x. So this will be 4 cosine 2x. Okay. Now if you see how the L'Hopital works, perhaps we can compare if we are trying to use some identity. If you check this cosine 2x, we can rewrite this as 1 minus 2 sine squared x, right? Now from here we have one minus okay, and then this is 2 sine squared x, and we can cancel this, and we have limit of x and 2 sine x. Well, if you get this, remember that we can rewrite this in terms of let me factorize 1 over 2 outside here, and we have x over sine x, right? X over sine x we can write as 1 over sine x over x, which is, this is equal to 1, right? And it's our answer is still the same, 1 over 2. So remember that whichever method that you are going to use, both are correct, and it's the preferable options is up to you which method you are going to use.
How do you get sine x over x again?
That's the property of the limit. So if you have limit as x approaching 0 of sine x over x, this is always going to be 1. This is what we call the definition, the limit definition of sine x over x. Because of this limit, we can derive sine become cosine because of this limit. Yeah.
I mean, what I don't understand is like in that step, right?
Mhm.
X cancel is equal to 1 over. Oh, I understand.
Okay. Yeah, just to remind you. But so whenever you have x over sine x, it's actually equal to sine x over x, which is equal to 1. Okay, another question related to limit. If you have limit as x approaching 0 of x squared cosine 3 over x with power 4. Okay, now if we look here, there's some confusion if we are going to evaluate x with 0. It's 0. It seems that this will be going to have an infinite factor, right? It seems. But remember, if we have cosine, whatever they may be in the structure, in the functions, every trigonometric sine and cosine, they always have maximum and minimum, always negative 1 and 1. Right? If you check with the graph and you're going to draw the graph, the x have certain domain. That's from. So if we are going to look here, we can try to prove this by saying that since the cosine itself will be between negative 1 and 1, and if we multiply this with x squared, and we know that the limit is equal with the limit is equal to 0, then by the squeeze theorem, that the limit is also 0. Okay, so squeeze theorem can help you to identify whenever you see a limit and you want to at least prove and make sure that the limit is between two functions that can be observed. Okay, that can be observed. Okay, so you can use the squeeze theorem.
also do with the sine, since sine and cos is.
Yes, the same with sine also. Okay, that's a little bit on limit. Okay, now if we look chapter 3, okay, chapter 3 is, we are going to have the derivative, right? The derivatives, okay. Of course, we start with definition using the limit, like I've written before, and also stated that differentiability differentiable, the function is differentiable or not. This will relate to conclusions that the continuous function, it's not the same as differentiable. Okay. To visualize or some pictures that can be easily to be analyzed is if we have like this. At this tip, we cannot differentiable. F of x is not differentiable. And how to prove this is we are going to use the limit again. Okay, the limit. So the limit from the right, and we are going to have, let's say we have this let me write this to check differentiable or differentiability. And the most, I think, important in derivative is the technique. The technique that I can assure you that the technique will be carried on in I think in the future courses, and I think you have experienced some of the techniques in the other course as well. Some of the techniques, the simplest one from the product rule, or maybe from the power rule, and then some trigonometric quotient rule here. Some logarithmic and exponent. And then we have product rule. If you have composite functions, quotient rule should be here. Sorry. Should be with the product rule. And then chain rule, implicit differentiation, okay, if we have questions, for example, asking, let me give you two questions. First is this. Second is this. It's 104, the second one. Sine 2x with power of 104. sorry. It's not a power. Let me write this in more clear. It's 104. So we are not going to find the first derivative, but this means that 104 derivative. So we are going to derive sine 2x 104 times. Every time you have the exponent, okay, you're writing the same exponent itself and then write the chain rule of the tangent, which is a secant squared x. I think not too difficult. For the second one, the question is asking 104 derivative of the sine 2x. So we can first maybe take some time to write several derivatives. Let's say the first one, take one time. This will be 2 cos 2x. And then let's say we have second derivative, we have 4 and then minus sine 2x, right? Or if you would like to see how the patterns, we are going to have this form. And then third time, minus sine become minus cos 2x, okay? And then when we are having fourth time, this will going to original, right? Back to original. So every fourth time we have this original. So when we have sine 2x with power of 104, 104 is, if we check with the with some 4 multiplication, it's also multiplied by 4. So we know that this will be going to turn back. The sign becomes the original one. So this will be our answer. And chapter 3, I think we were just focusing for chapter 3 on these three, all these elements of the techniques and the definition. Okay, definition, differentiability, okay, for the midterm. Let me check. let me check if you get this correct. We have f1 plus x 1 minus x is equal x. Forget whether I have this before.
Also, I don't understand the question.
Yeah. This is the equation. The equation, so f of this 1 plus x over 1 minus x is equal to x. So the question is actually asking the f prime of 2. So of course it's obvious it should be x, and f of x, when x equals. So first you need to think on what is this relation. It's I believe it's more advanced questions that you need to think in terms of how we can connect this 1 plus x over 1 minus x with x. Let me give you a couple minutes to think, okay, to think how this is going to result. What's the results? So first, for obvious reason, you need to find the function itself, the f of x. That's the one that you need to find. Remember that this is not okay, this is inside the functions. The idea how to solve? Okay. Okay, the keywords to solve this is inverse. Okay. So we can connect this to with inverse. So we are going to exchange this part to x with inverse. So we are going to write down that the inverse is equal to this. Okay, now to make our calculation easier and to make yours also easy to see, let y becomes f prime f inverse. Okay. So let me write y. So when we need to find the f of x, we need to exchange y with x, right? It's like usual inverse. So we are going to have y minus x, y, 1 plus x, and then we are going to solve in terms of x. So x plus xy and y minus 1. So we will have x, y minus 1 divided divided by y plus 1. So based on this relations, then we have f of x is x minus 1 divided by x plus 1. Or we can write this y inverse is, okay, and y inverse is f of x. Now we can directly derive from the equations with quotient rule. However, if you want to take some time to rewrite the form, we can also rewrite the x minus 1 divided by x plus 1. We can define, and we can exchange this into 1 minus 2 over x plus 1. Okay, this is also similar. I think this way you can derive, I think, much more easy. Okay. To avoid this negative positive. Okay. So this will be resulting in 1 over x derived becoming negative 1 over x squared. It has negative, so negative will be gone. So we'll have positive x plus 1 squared. And when we have 2, then this will be 1 or 2 over 9. Okay, to maybe make sure that we understand our steps here, let me just go here to see what's exactly going on here. So it's actually just regular division. So this will be 1, x plus 1, and we subtract this. This will be negative 2. So we will have 1 minus 2 over x plus 1. Okay, this is what we have. Okay. And if we want to derive 1 becomes 0, negative 2, and then d dx of 1 over x plus 1. 1 over x plus 1 is basically we derive x plus 1, negative 1. We are going to have negative x plus 1, negative 2, in which we have negative 2, negative 1 over x plus 1 squared. And then that's how we can get it's positive. Okay. Yes?
How can x minus 1 minus x plus 1 equal to negative 2? Here, I mean this part. This part you divide it, right?
Yes.
But this one can go one part,
yes,
and you have this with this equal to this, right?
Yes.
But how can, and you use this minus this,
Yes.
equal to negative 2, but how can it be?
Negative 1 minus 1.
Oh, okay.
Okay.
Right, right. Oh, yeah, perfect.
Okay, let's see other example. Okay, let me go through. if f is differentiable on all real number, then AB is, okay, so basically we need to find the constant of A and constant of B. So if we perhaps look on the interval, we know that there will be a number, right, that we are going to approach from the left or from the right. But then we assume, or we are having some predictions that that number is important. Okay. So first, if we look on the question here, we have two equations, and we have the interval. They are having 1, so we should consider 1 as our target approach for x. Okay. So let's write down the definitions and how we can have the differentiability. First, of course, it should be continuous functions. We can write f continues at, it should be continuous, right? If not, then we don't have any more steps. And second, let me write okay, maybe write like this. Okay. Now from these two requirements, we can set differentiable. Let me finish a little bit and then we can have a short break. So first, when we have limit, we will have that implications. This is A equal with 1 plus B. Okay, this is the first implication from the continuity. From continuity. Okay. Now second, this means that if the derivative at 1 from the left, let's say this is first derivative of when x equal 1 from the left, and from the right should be equal. So this will be 3a equal to a, oh wait, why 2a? Just 2x, right? 2. So a will be 2 over 3, and b will be 2 over 3 minus 1, or negative 1 over 3. So a, b will be 2 over 3, negative 1 over 3. Okay, and then perhaps another some typical question or some essential one is about the tangent line. So tangent line, let me just give you directly the example. So tangent line to the curve. is equal to this is 3x cubed. So let me give you a couple minutes to check.
Anyone find? Okay, first maybe understanding the questions will be maybe a better approach. So sometimes you see equations, if you remember, the tangent line means that if you want to find the tangent line to the curve, then we set the curve as our equations, and it seems that because it has x and y interchangeably in one equation, we will know that perhaps to know the equation of tangent, then we need to take the implicit differentiation of it. Okay. Now, if we take the implicit differentiation, what's the relation with the tangent? Remember that tangent, or the gradient, the slope, is the dy over dx, or the first derivative, right? So if we can find the first derivative out of this equation, then we can find the tangent line. Okay. The first derivative is specified at this point. Okay. So first, without any, sometimes when you derive, for example, this implicit, you are going to derive and make dy over dx into some set of equations, right? So before you are going to do that, if you already derive this implicitly once, before you simplify, you just you just put in this point, because I think it's easy number 1 and 0 to x and y, and then you will get directly dy over dx, and this will shorten your time. Okay. Regarding so let me write this for you here. So implicitly, or maybe if we write let me write all, and then implicitly derive. And then 3x squared plus 2y dy over dx. Okay. Now, at 1, 0. So we are going to exchange all x with 1. This is 0. And then we have 2x is 2, 1 plus 2, and then 0 equal to 3 plus what's this? Y is 2. It should be y, sorry. Plus yes, okay. Okay, I think it's correct now. So dy dx. So because this is getting 0, so everything going to be 0, right? So we'll have dy over dx equal to -3. Okay. And then the line would be y minus 0 equal -3 x minus 1. Or we are going to have plus 3. This is our tangent line. Okay, now we move to chapter 4. Okay. So chapter 3, that will be the essential problems and some techniques that might be useful. And as for the midterm exam, I think I will just focus more on chapter 4
And then the second priority is chapter 3, and then the last one is chapter 2. Okay? So, for example, in chapter 3, we have the related rates, right? So I think I will just skip the related rates. Okay, so no questions about related rates on midterm. But rather, we will move to chapter 4. And I think we will have at least the optimization. Okay? I hope you still remember. And sketching the curve, that will be, I think, important. But before we are going to look on to the questions, chapter 4, we deal with the application of derivative, right? This will include mostly is sketching the curve and observe the graph. Okay. So we start with the functions f of x. Okay. Of course, from the function itself, we can know what is the domain, what is the range, right? And then whether it has asymptote, we have vertical, horizontal, and the slant asymptote, right? The vertical asymptote we are going to check using the limit. If we have some a, okay, and then when we deal with the limit, we will have infinite point or negative infinite. And horizontal is when we're approaching x to infinite or negative infinite, it will go to some L. A slant is when we have a typical line. That is, if we have limit, when we are going to have, for example, or maybe let me just write this in terms of usually this is let's say G and then Q. Usually this X as X will be a slant. Usually. Okay. And then from the asymptote we have the f prime. Okay. The first derivative test. This is to see increase and decrease. So when f prime x is positive, it's increase. When f prime x is less 0 or negative, it's decrease. And we deal with the critical point from here. Usually critical point is equal 0 or f prime x doesn't exist. And from here, we are going to have the second derivative. The implications, we have concave upwards and concave downwards. This is when it's positive, upwards when positive, and downwards when it's negative. And then another terms that's important is inflection point. Usually, inflection point is when the second derivative is 0, but not always. We know that inflection point will be when concavity change, either from the upwards to downwards or downwards to upwards. Another essentials in chapter 4 includes the indeterminate form, the L'Hopital rule. We have done in previous slides. And the other part that is important in chapter 4 is the optimization. Optimizations and the antiderivative. For optimizations, I hope you still remember how we can solve the problems. We have the formula, derive, find critical point. Okay, we start with the diagram, formula, derive, and critical point. Find the critical point. Antiderivative, at least you know how the relations between f, the original functions, and its derivative. And then it's better if you can imagine this in terms of how the graphs looks like. Okay. Okay, perhaps we can go for some example. Okay. Maybe start with questions regarding the this one. So we start by looking at the graphs, and the graph is actually the first derivative. Okay. There are 4 questions. On what intervals f increasing, decreasing, and then local maximum, local minimum, and sketch the graph of the second derivative, and sketch of possible graph of the original functions. Now, what you need to take it as essentials is all the f prime, f double prime property. When it's positive, when it's negative, what it looks like, increasing, decreasing concavity, okay, critical point, and then the inflection point. I think if you
take that as your essentials for any sketch curve or any observation of graph. I think based on what you will write in the question or in the answer sheet, then I think it's okay. It's okay. Perhaps we start with A. When f is increasing?
0 to 2.
0 to 2.
1 to 7.
1 to 7. Okay, good. 1 to 7. That's when increasing. Do you know why? Remember, if you say 0 to 2,
Okay, I understand.
you see that if you see the graph, it's increasing, but it's not the f, it's f prime. So we need to stick on the definition of f prime. Okay, so f prime, we need to stick on that if this is positive, then will be increasing. And if this is negative, then this will be decrease. Okay, since on the 1, 2, 3, 4, on 4, it's actually touching the axis. To write it in more clear, we can write 1, 4, 4, 7. I think it's more safe. It's safer. So increase, this will be on 1, 4, and 4, 7. And then decrease is 0, 1, and then 7 and 8. Okay. Okay, and then local max, local min. This is from negative to positive, and then positive to negative. So we will have at 1 and at 7. At 1 it's going to be like this, at 7 it's going to be like this. So local max is x equals 7, and local mean is when x is equal 1.
I don't understand, Professor.
Yes?
At first I thought that local max is the highest point, but no. At first I thought that local max is the highest
But
point.
this is x prime,
Oh.
and it doesn't mean that it should be the highest. What max min means, this shape. You see that it's negative to positive, so it should be going down and then going up. Positive, negative. So it's going up and going down. It should be having some, like a mountain, right? Like a mountain. So that means that it's going to be local max. Okay? Okay, the C and D, let me draw the graph here. Okay, I hope that's... So let me name, this is 0, 2, 7, okay. Okay. Now we need to sketch the second derivative for C. Okay, so if you have f prime here, when we need to write the f double prime, then we need to derive one time, Means that the idea of second derivative or the derivative of a function from this one, the first derivative of f prime, means that we are going to see this first the slope. I think that's the better way for the first impression. How the slope will be. We see the slope is changing here, okay? And then I think maybe start with the slope that is 0. I think that will be better for first step. This is slope is 0, right? Also 0 here. Also 0 here, right? So we can start by looking at the slope. You can write that this is going to be 0. Means that at the graph, when we are going to graph this, at this 2 and then 4 and also 6, the curve will crossing, right? Crossing. And then when you see the concavity here, I think in the 1 is changing its concavity. So 1 will be it should be going to be let me change this color. So 1 will be here. So this will be going to up here and going down, crossing that. And at 3, you see 3, this is also changing its concavity, right? From this downwards to upwards. So probably that will be the inflection. So the inflection means in our graph, it's going to be different color. Maybe that, and then to x equal 4 is crossing, okay. And then we have also at 5 is also changing from upwards to downwards from here. Okay. So maybe here, and then 6 we need to cross 6, so 6 will be there, and then 7 also changing the concavity. Okay, maybe I think that's enough. I think. So first, let me write here. First, check the slope when slope is equal to 0, and check the inflection point. And now we need to check the original graph. Maybe let me put this a little bit down here.
put some graph to see. Sorry. One, two, three, 4, 5, 6, 7, 8. So how do we deal with the f of x? First, that we see some x equal 1 and 7, and also I think it's 1 and 7. That will be since 1 and 7. So f prime x equals 0 at x 1 and x equals 7. And since the this is negative to positive, okay. So means that from 0 to 1, it's decreasing, right? It's decreasing and then increasing. So it's decreasing and then increasing. Okay? It's decreasing and increasing. So let me take a little bit longer here. So it's decreasing and increasing. This is 1. Okay. See that this slope is negative and positive, right? And then at x equal 2, it's going to be 0, right? So probably we have this is still positive, still increasing until 4. So 4, maybe 4 is around here. Okay, this is 4. So it's still increasing until 4. So increasing, and still after 4, it's still positive, right? So it's still increasing. So we are not going down, it's still increasing. But maybe a little bit stationary at this x equal 4. It's still a little bit stationary, means that the slope is 0, but still it's increasing. Increasing until 7. Where is 7? Let me draw the 7 here. Increasing and until 7, and then after 7 it's going to be minus, so it's going down. So that will be our y equal f of x. Okay, so the idea, see the slope. That's the essential. So this, see the slope. And the meaning is, you need to remember what's the meaning behind the f prime, f double prime, okay? And when the curve has local max, local mean, okay? When it's increasing, decreasing, and when the slope is 0, what's the meaning of that? Okay. Let me check the time. Okay, we still have time. Maybe one or two questions related to the chapter 4. Maybe I will give you 2 or 3 questions, additional video later on after the class. So we try our best to solve. Okay, let me give you another one. Let's see, number 63. This is from the optimizations problem. The question is asking what is the shortest possible length of the line segment that is cut off by the first quadrant and is tangent to the curve y equal 3 over x at some point. So perhaps if the question seems confusing, means that first maybe you want to draw the curve first. Draw the curve. And then there is a tangent line of the curve here at some point. There's a tangent line. The tangent line will cut off the x and y axis. Okay. So maybe I will help you to see from the drawing. Okay. If this is y equal 3 over x. And maybe this is the tangent. Okay.
So it's asking what's the length of this? So we need to find this length, okay, through the tangent line from this equation. Okay. So you know the x and y intercept, okay, from the equation and from the point itself. Okay.
So you use you have y and x. This for sure. Okay.
So you need to know y and x to know the distance between these 2 points.
And then how we can solve this?
Differentiate.
Yeah, differentiate for the tangent, right? Find the tangent. So maybe let's make a point here. Let's make a point.
It can be any variable you can think. Maybe b, a. Okay. Let me put this as point a, x equal a, and then y will be 3 over a, right? Because it's on the curve 3 over x. Okay. Now, if we have y equal 3 over x, the first derivative to take it for the tangent line is negative 3 over x squared. Okay. So at x equal a, this will be negative 3 over a squared. That's our tangent at A. Now the tangent line, we can input the line equations. Y minus 3 over A is equal minus 3A squared x minus A. We can solve this, and then plus 3 over A plus 3 over A is plus 6 over A, right? And then from these equations, from these line equations, we can get our y and x, right? We can take y equals 0 and x equals 0 to check the intercept. Okay. So let me check. When y equals 0, negative 3a squared x plus 6 over a is equal 0. So negative 3x a squared is negative 6 over a, or we can cancel this. So 3x is 2. So x equal 2a, right? When x equals 0, this will be y equal 6 over a. So we can write down that y is 6 over a and x is 2a. And then the optimizations, what we need to find, we need to optimize. So we haven't got into the optimization. This is just the introductions, okay? How to find which way we are going to optimize. So the optimization itself, we are going to have our distance will be square root of both intercept, so 2a minus 0 plus 0 plus 6 over a. So this will be 0, 6 over a. This will be 2a, 0. And we find the distance formula from there. Okay. Since it has square root, so this is my suggestion. Every time you have a distance, you have a square root, right? To make it easier to analyze and observe, and because it's a positive function, because the distance should be max, the value should be positive, we can take its square so that we can remove the square root. So it's better for calculations. So we can take maybe some s as our d squared. Okay. So s will be 4a squared plus 36 over a squared. And then from here, we can derive and find the optimization. So let me write s prime is 8a minus 72 a cubed, right? Minus 2 minus 3. And then take it equals 0 to find the critical point. So we will have, so a with power of 4 is equal 9. A squared is 3, and a will be square root of 3. We are going to focus on the positive value, okay? And then we can check s double prime, okay? Check s double prime. If this is greater 0, we will have the minimum value, and you can make sure that this A is our minimum value. So we will have the S, or maybe we can take S 4 square root of 3 squared plus 36 over, or S will be 24. Or in our case, our D will be, so we bring back the original question, which is D. Okay. It's a little bit complex, okay? But when you see what we are going to find and how we are going to find it, I think it's actually okay. So the essential point here is we need to find through how we connect this, okay, and find this length. Okay. So whenever you find any length in a graph and you want to optimize it, usually we are going to focus on the distance formula. Okay? And since it will be positive, we can make some simplifications and make our own model to simplify the calculations so that we can easily calculate. Okay, I think that will be the last question, but what I want you to perhaps helping you solving several problems. Maybe you can try to focus on checking this number, okay, for just these 4 numbers, okay. That is just for practice, okay, for practice. So check how to sketch the curve of this 4, and I think that will be helpful for your midterm. Okay. I think that will be our conclusions. Okay. So